Welcome to day 36 of the STL Mastery course. In this lesson, we will explore how the standard template library STL can be used in real-world application design. STL isn't just for academic exercises or coding competitions. It's a critical tool in scalable and efficient application development across industries. Today, we will look at how to structure real systems using STL containers, algorithms, and techniques to solve real-world problems. Let's jump in. By the end of today's session, you will be able to integrate STL into your application designs effectively. Especially, you will learn how to leverage STL to optimize performance in real-world systems, combine multiple STL components in a structured, efficient way to meet your application's needs, make design decisions by choosing the right containers and algorithms for the right use cases, explore how STL is used in real-world open source projects, allowing you to see how these concepts are applied in industry. So let's get started with some foundational understanding of how STL fits into real software engineering. STL is not just an academic tool, it's an integral part of real-world software engineering. STL is widely used in industries like gaming, finance, embedded systems, and web development. For example, game engines rely on STL containers for efficient data management, and fintech applications use it for high frequency trading algorithms. Even web servers use STL to manage large amounts of data quickly and effectively. STL helps solve real world problems by providing optimized data structures and algorithms that can handle complex, large scale applications. In modern software design, modularity is key to scalability and maintainability. STL supports modular design by offering flexible containers and algorithms that allow us to decouple different parts of the application. For example, in a task manager application, the data layer could use a map to store tasks by name, and a multi-map could be used to store them by deadline for easy sorting. For managing task priorities, a priority queue could be used. A stack or vector might handle undo actions, storing previous task states for recovery. This modular approach not only ensures that each part of the system is optimized for its task, but also makes it easier to scale as the system grows. Let's look at a real-world example, a task manager application. Imagine you need to manage a list of tasks with the ability to add new tasks, sort them by deadline or priority, search for tasks by keywords, implement undo, redo actions. For this, you can use STL containers like map, string, task to store tasks efficiently by their name. Priority queue to always retrieve the highest priority task. Stack action to implement an undo or redo system. Vector to keep an ordered list of tasks based on a certain attribute. This combination of containers ensures the system is both efficient and flexible. Here's a high-level architecture of our task manager. We can structure the application as follows. Task storage. A map string task allows us to store tasks by name, providing log and lookup times. If we want to track multiple tasks with the same deadline, a multi-map date task could help us manage them in a sorted order. Undo functionality. By using a stack action, we can push every change to a stack, allowing us to pop the last action when the user hits undo. This ensures we can easily revert the state. Priority-based task sorting. A priority queue can help us always retrieve tasks in the order of their priority level, ensuring that critical tasks are addressed first. This architecture keeps our code clean, decoupled, and ready for future enhancements. A key to designing high-performance applications is choosing the right container for the right task. STL offers many options, and understanding the trade-offs between them can significantly impact our application's efficiency. For example, unordered map is faster for lookup operations than map because it uses hashing instead of sorting, but it does not maintain the order of elements. Vector is cache-friendly and efficient for random access and iteration, whereas list is optimized for frequent insertions and deletions. DQ is useful when you need fast insertions and deletions at both ends, unlike stack, which restricts access to the top element only. Choosing the right container depends on our application's requirements, such as the frequency of operations, memory usage, and performance needs. Performance tuning is essential when designing real-world systems. STL provides several tools to optimize performance. Using reverse fill factor helps minimize unnecessary reallocations when elements are added, improving performance for large data sets. Move semantics can avoid unnecessary copies of objects, making your application more memory efficient and faster. For operations that need fast access, vector is often preferred, while for random insertions, list may be more suitable. Lastly, STL algorithms are designed to be highly optimized, often outperforming manual loops or custom implementations. By carefully considering performance at the container and algorithm level, we can make our application both fast and scalable. STL is widely used in several major open source projects. For example, Git, the version control system, uses STL containers in its index and TIFF modules to manage and compare large datasets efficiently. OpenCV, the popular computer vision library, relies on STL containers like vector and map to store and process image data efficiently. Game engines uses STL containers such as unordered map and priority queue for tasks like pathfinding and game state management. These real-world examples demonstrate STL's versatility and power in solving practical engineering challenges. Now it's time for you to apply what you have learned. Your hands-on project for today is to build your own task manager application using STL. You will need to implement features like adding tasks and sorting them by priority using map and priority queue. Implementing undo redo functionality with stack to track changes. Optionally add a tag search feature using unordered multimap. This project will give you a practical understanding of how to integrate STL into a complete application design. To summarize what we have learned today, STL is a powerful toolkit for real-world applications. By choosing the right containers and algorithms, you can build highly efficient and scalable systems. Containers like map, vector, priority queue, and stack can be combined to solve complex real-world problems. Performance can be optimized through careful container choice, move semantics, and effective use of STL algorithms. STL helps us write modular, maintainable, and high-performance code. Your assignment for today is twofold. Build a personal finance tracker. Use STL containers like map, multimap, and stack to manage financial transactions and generate reports. This will help you understand how to store, organize, and manipulate data effectively. Research STL in open source projects. Choose an open source C++ project like LLVM or OpenCV and explore how STL is used. Summarize its role in various modules and how it contributes to performance and design. This exercise will deepen your understanding of STL's applications in real-world systems. That concludes day 36. Today we explored how STL can be applied to real-world software design, from task management systems to performance tuning. The tools you have learned today are the building blocks for designing scalable and efficient systems. Don't forget to complete your assignments, and I will see you in the next lesson. Keep coding and stay curious.